To finish up the theory of dimensions of affine varieties, we can look again at this definition of the hypersurface, which was an irreducible affine variety inside some ambient variety, such that this has some pure dimension and this has pure dimension 1 less. Again, this here. And we have seen that when x is irreducible affine and y is the vanishing locus of some non-zero function on x, then indeed y is a hypersurface by Kroll's principal ideal domain theorem. But the question is, what about the opposite direction? Is it also true that if you have something of dimension 1 less, then you can cut it out by a single equation? Certainly, if that is true, it's very useful because it tells you purely from these dimension considerations, you know a priori that you can cut out y by specifying a single equation. And it turns out the answer to that question depends on whether the ring of functions on x is unique factorization domain. So for this, recall that an integral domain R is a unique factorization domain, or UFD, if any non-zero x in R can be written as x is a product of a unit with finitely many elements, P1 up to Pn, which are irreducible in R. And moreover, these Pi are unique up to permuting them and up to maybe multiplying by units. So we can maybe draw in the unit into one of these Pi, if you like. So that is a purely commutative algebra characterization of some integral domains. And then we can have a proposition, and that could have been a proposition also in commutative algebra, but we're doing it now because now we have also some geometric interpretation of this. So it says, if R is a Noetherian integral domain, like for example, R could be the coordinate ring on some irreducible affine variety, where irreducible guarantees that we're an integral domain. Given such an R, the following are equivalent. So first, every prime ideal in R of height or of codimension 1 is principal. So it's cut out or it's generated by a single element. And B, R is a unique factorization domain. And so applying this in the above setting, well, the prime ideals P inside AX of height 1, they just correspond, prime ideals correspond to irreducible varieties, irreducible subvarieties of X. And the fact that it's of height 1 means the corresponding variety is of codimension 1. So it is a hypersurface inside here. And then translating this result, here it says that if R is a unique factorization domain, so if the part B is satisfied, then each such hypersurface is has an ideal generated by a single function. And so in other words, y is the vanishing locus of this single function. So this would show the converse direction above here. And so for the proof, well, you do have to work a bit here, and that's kind of standard commutative algebra. But so we start with this direction, A implies B. So we want to show R is a unique factorization domain using this property here. And so let's start by saying, well, if you're given a non-zero f in here, then you want to factor it. And we can do that by either, well, by observing that either f is irreducible, and then we're already done, and we just have f is equal to 1 times f with f irreducible. Or, well, if it's not irreducible, then it is reducible, so f is the product of two things. And then we can continue. If F1 and F2 are reducible, then we're done. Otherwise, we decompose them further. And very similar to the proof that showed that a Noetherian topological space has an irreducible decomposition, we can see that from the fact that R is Noetherian, that there's no infinite ascending chain of ideals. Very similar arguments show this process cannot continue forever. It can't be that we continue decomposing F1 to more factors and their factors into more factors. But so it has to stop. And so at some point we have decomposed F into a product of irreducible elements. And note, until now we haven't used our assumption A. So this only works. This works only using that R is Noetherian. And then the big claim is that for this decomposition, actually all of the Fi are prime. And then kind of let's assume we had this claim. How do we finish the proof? I propose that if we know this, then this implies the uniqueness part of the UFD definition. Recall that, I mean, we have to show this F can be decomposed as such a product where the Pi are irreducible. This we have already done. Yeah. And now we just need to show that they are unique up to permutation. And so if we knew that these Fi were prime, assume we had another decomposition into irreducible things, then the same argument would show they're also prime. And now we do again something very similar to the irreducible decomposition of Noetherian topological spaces. We say, well, for example, start with the F1. This is a prime element, and it certainly divides F, and F is then also this product here. So F1 divides this product. So because it is prime, it must divide one of the factors. Let's say it divides this one, F1 prime. Then we turn the thing around and say, well, F1 prime is prime. It divides this product, so it must divide one of those things. And then, well, we can assume, I mean, of course, the nicest thing is F1 then also divides F1, because then we have a chain, F1 divides this, and this divides this. And this then implies that these two things must be equal up to units. For this, I mean, you should convince yourself of this by just writing down what does it mean for this to divide this, for this to divide this. But that's just a short argument. In general, in this case, it could happen that F1 divides this and this divides something else. But then, of course, F1 also divides this thing here. And we could still use such an argument to basically show that F1 and F1 prime are related up to unit. And then we would be allowed to remove this and this here, maybe up to changing unit. And then we would be left with a decomposition with fewer factors. And then we could conclude the result by some kind of inductive step. So I was a bit sketchy here, and I mean, you should convince yourself of this. What I can say is that in Gartmann's notes, actually, he defines a unique factorization domain as something such that each element here can be decomposed like this with the Pi prime. This is a stronger condition because each prime is irreducible. But then, in fact, defining it like this allows you to just omit the second definition, because by the argument that I explained now, it then follows automatically. In a certain sense, his treatment is more efficient. In either case, we are left with proving this claim, which then finishes the uniqueness part of the UFD property. Okay, so now you just need to look at this claim. So we want that in this decomposition into irreducible factors, all of the factors are prime. And we just show that in fact all irreducible elements of this ring will automatically be prime. So fix one of the Fi and then choose P inside R, a minimal prime containing this function Fi. Then by Kroll's principal ideal domain, the codimension or the height of this prime ideal is equal to 1. And now we're in business because now we have a prime ideal of codimension 1. And so we get that P is generated by a single element F. And since it is a prime ideal generated by a single element, that element must actually be a prime element. This is the relation between prime elements and prime ideals. And so we can conclude now by observing, well, the Fi was contained in P because P was a minimal prime ideal containing it. So Fi in P. So this means Fi must be a multiple of G. In other words, G divides Fi. But now this Fi was chosen to be an irreducible element. So it can't be that Fi is equal to A times B, where A and B are somehow, it can't be that Fi is equal to G times G tilde, where G tilde is anything but a unit. And so we conclude that Fi up to unit agrees with G, and G was a prime element, and then multiplying by a unit doesn't change this, so F or Fi is a prime element. Okay, so this was a slightly tricky argument, I would say, but basically it was one of these commutative algebra proofs where you just kind of move things around until things fit. So for the other direction, now we want to show if R is a unique factorization domain, then every prime ideal is principal if it has codimension 1. And so we fix P inside R, a prime ideal of codimension 1. And then, well, P is a strict ideal in R. And I claim we can assume without loss of generality that 0 is also a strict ideal in here. If this is not the case, if this wasn't strict, then, well, P would be 0. And then it is still a principal ideal, what we want to show. So we would also be done already. So we can assume without loss of generality, this is a strict inclusion. But then having this as a strict inclusion, well, we can choose a non-zero element, F in P. And since P is not all of R, it means that F is not a unit. Because, well, if we had a unit element in our ideal, then the ideal would have to be the entire ring. Okay, so we have gotten ourselves a non-unit element in the prime ideal. And then we are proving this direction, so we can assume R is a UFD. And so this element can be decomposed into irreducible factors. And in fact, by that argument which we have seen, any irreducible element of a UFD is, in fact, a prime element. That's something which is true in general, and which we have maybe seen in the commutative algebra lecture. And so we have decomposed F into a product of primes, in fact. And now this original P, the prime ideal that we started with containing F, is prime, and F is in there. So this product of elements is in the prime ideal. By definition of prime ideals, this means one of those, so there exists an I, such that the Fi is in the prime ideal. And now we have gotten ourselves an interesting sequence of ideals. Well, the 0 ideal is strictly contained in Fi because Fi is non-zero, otherwise F would be 0. And Fi is contained in P This was what we how we chose it. And so now we have a sequence of kind of 3 prime ideals inside this codimension 1 prime ideal P. And normally, I mean, that would be a contradiction, except that, of course, we don't know. So this is strict. And so if this was also strict, then the codimension of P would be at least 2. So since this is not the case, we know this cannot be strict. It must be an equality. So Fi is equal to P. And so we have shown that P is principal. Okay, so this was essentially a purely commutative algebra statement, but it allowed us to have this kind of nice observation that inside a variety X whose coordinate ring is a UFD, we know that every hypersurface is cut out by a single equation. And then you might ask, like, what about an example where this is not satisfied? So where R is not a unique factorization domain, then there should also be a prime ideal, which is non-principal. And this is a very concrete example. And it's a great source for pathological behavior. So we're going to see this particular example a couple of times. The ring R that we consider in this example / exercise is the quotient of this polynomial ring in 4 variables by this equation here. And then you can show, first of all, this is an integral domain of dimension 3. That kind of fits. You started with something of dimension 4, impose a single equation. All of the x1 up to xn, these are all irreducible elements, but it turns out they're not prime inside this ring. This already tells you that R is not a UFD. Another way to see it is that, well, the elements x1, x4, and the element x2, x3, they are equal because, well, the difference is divided out, quotiented out here. So they are equal and they give decompositions of the same element in the ring R, which do not agree up to permutation and units. So here we saw they're irreducible, but we also see it's not the case that up to maybe shifting some units back and forth and up to permuting them, these 2 decompositions are equal. And so that's an explicit counterexample to the property of R being a UFD. So we are very convinced now R is not a UFD. Now we want to get our hands on some prime ideal of codimension 1, which is not principal. And indeed, in the next exercise part, you see that if you impose the vanishing of x1 and x2, then this is a prime ideal. And you can check it is of codimension 1 in R. And the claim in part D is it is not principal. And then going to the geometric side, well, you have the vanishing locus x of this polynomial here. The coordinate ring will be exactly this quotient. And it contains the vanishing locus of these 2 variables, which we call y. And then so y inside here is, the claim is this is a hypersurface in there. So dimension is pure of dimension 1 less than x. And also its ideal cannot be generated by a single element in AX. So, so that basically concludes the exercise. You see here the exercise lays something slightly stronger than we would have liked maybe. So somehow this says the ideal of y cannot be generated by a single element. It could still be at this point here that there is a single element in the coordinate ring of x which cuts out this space, but maybe doesn't generate the ideal. Because, I mean, the ideal would then be the radical of the ideal generated by this one element. So it could be, we might still have some hope at this point that at least as a set, we can cut out y inside x by a single equation. And in fact, that turns out to also not be true. So everything goes wrong in this example. The y is not cut out by a set by a single equation in AX. In other words, there's no g in AX such that y is equal to the vanishing set. And this is not discussed in Gutmann, but this is discussed in this book by Ravi Vakil called The Rising Sea, which is a great source for learning algebraic geometry, but follows a slightly different approach than our lecture. And there you can find it in exercise 15.4.t. And you see it is exercised in section 15 of the notes, so it uses a bunch of techniques. And in general, I would say about this example here, this is a challenging exercise because you need to have some kind of creative ideas for proving all of these properties. My hints here is that a lot of these properties can be proven using that this here is a graded ring, where the grading of each of these xi is equal to 1. And that can often help you show that maybe there's no way to decompose something in a certain sense. The other property that you can use if you have seen the Zariski tangent spaces, maybe in the commutative algebra lecture, then this is a very powerful tool which can help you show these results. And this is also what Vakil's exercise recommends using. Okay. But so here we have seen an example that if the UFD property fails, then we can have hypersurfaces not cut out by a single equation, not even as a subset. And returning to a bit more nice ambient spaces, we can now apply what we have seen before to hypersurfaces in AN, in affine space, which is certainly very nice. So somehow, let's assume that X inside AN is a hypersurface. Then we can decompose it into irreducible components. And then we see this, the ambient space, has coordinate ring R, which is the polynomial ring in n variables. And this is a unique factorization domain. Again, a statement from commutative algebra. And then the proposition tells us that, well, this I of any of the vanishing ideal of any of these irreducible components, it is a prime ideal because the components are irreducible, and it's codimension 1 by Gross principal ideal domain, principal ideal theorem again. And so we have a codimension 1 prime ideal, and then the proposition we've just shown tells us that it is principal, so it's cut out by a single polynomial, which is a prime element of this ring here. And then by the standard properties of ideals, we have that the ideal of X is the ideal of this union here, and that's the intersection of all of these principal ideals. And then using the fact that the Fi are all prime elements, which are also different, and they don't, the fact that this is a minimal decomposition means none of these Fi divide any of the other Fj. And from that, you can see that these intersection of ideals is the ideal generated by this product. And let's call this product F. So then we have concluded that also the ideal of this possibly reducible hypersurface is still a principal ideal. And I mean, if you follow all these uniqueness parts of the UFD, you can also check that this product F is unique up to units. And so this means if you're given affine variety, which has dimension 1 less than its ambient space, then you can find this unique up to units element which generates its ideal. And you can use this, and this is the final thing in this video here, you can use this to define the degree of such an affine hypersurface. So if X is in AN is a hypersurface, and its ideal is generated by F as above, then you call the degree of the hypersurface to be just the degree of this polynomial here. And then for different degrees of X, you call these hypersurfaces differently. So if the degree is 1, then it is a linear hypersurface, sometimes also called hyperplane. When the degree is 2, it's a quadratic hypersurface. And 3, it's a cubic hypersurface, and so on. Sometimes these are also called quadrics and cubics, and so on. And this justifies, in the last video we have seen this hypersurface cut out by a cubic equation, and then indeed for most of these cubic equations this will in fact be a cubic hypersurface, because that equation is the minimal generator of the ideal of its vanishing locus. That was everything about the dimension theory, and that's the end of the video.